Katrina here, and today we're going to dive into probability functions. We're going to look at probability mass functions and probability density functions. Be sure to watch to the end so you can get all the information you need to ace your next exam, and please subscribe for more videos. So in my last video, I talked all about random variables. We learned the difference between continuous and discrete random variables. We also learned that random variables, contrary to its name, is actually a function that maps an outcome from the sample space to the real line or the target space. So now we're going to see the relationship between these random variables and the probability functions. So the first one we're talking about today is the probability mass function. So you'll more often than not see this abbreviated to PMF. So the probability mass function goes hand in hand with discrete random variables. So recall that a discrete random variable is finite or countably infinite. So some examples are a number of kids in a class, the number of plants that you have in your house, and this would also include integers and whole numbers. So let's define what a probability mass function means mathematically. So a PMF of a discrete random variable x assigns probabilities to the possible values of the random variable. So more specifically, we can say that if we have these little possible values, so if we have x1, x2, x3, for example, which are the possible values of our random variable x. So these are possible values of our random variable, and we denote that as our capital or bolded x. So again, remember that the capital X, our random variable, has many possible values, right? Because it's mapping everything from that sample space to the real line or the target space. So each one of these, x1, x2, x3, ... are all possible values of our random variable. So if that is the case, then that means we can denote our probability mass function in the following way. So let's give ourselves a mathematical notation. So we can write it, looks like function notation. So this is p of xi. So this xi represents our, our x1, our x2, so on. And this can also be written as capital P, where the random variable, large X, equals to that specific outcome, right? And then that equals to the probability, where here we have our small s, which is an element of our big sample space. So this is an outcome in our sample space, such that x of little s equals to xi. So this is just a fancy way how to write that. What this means, this over here, let's give a little deeper dive into that. So that there, let's just scroll on over. So this is the set of outcomes resulting in our random variable x being equal to that specific outcome. So just note that this notation over here, p of xi, is the shorthand for this one. You often won't see this large one at the end, but I just want you to have that in your book so you can really see that we're looking at specific values within a larger set, and you can see the full notation. So this means, like we said over here, it represents the probability of the event that the random variable, big X, equals to our specific outcome, xi. So the probability of the event. So we're going to be using the word event a lot in probability. So it is considered an event when our random variable equals that specific possible outcome x sub I. Okay? So this is our formal definition of our probability mass function. So now let's look at some of its properties, because it's important to understand the properties because there are some criteria that have to be met in order for us to use this equation. So remember that x is discrete, so that is very important. This only works for our discrete variables. And also remember that our x1, x2, so on, are our possible values. So this is kind of our new kind of notation, new words that we need to know when we're in this world of probability, because it works a little bit differently than our regular world of math. Okay, so let's write this out. So the probability mass function of x, or PMF, is denoted as our P, right? We said is our P of xi. This is our PMF. So it must satisfy the following. So the first thing that it has to satisfy is that the sum over all our xi, over all our possibilities, the sum of the probabilities here, so this is our P of x1 plus P of x2, so on, must equal to 1. So the sum of all our probabilities have to equal to 1. That means that you can't have a probability, so our sum has to equal to 1. So the sum cannot be greater than 1. We can't have a sum of over 100% or a sum of less than 100%. Think of our heads and tails example. We have technically a 50% chance of getting a head and 50% probability of getting tails. So if we add 50 plus 50, we have our 0.5 plus 0.5, that equals to 1. So the sum of those probabilities equals to 1, okay? So let's move on to our second condition. So our second condition is that our probabilities have to be greater than 0 for all of our xi, and then similarly they have to be less than or equal to 1. So we can write this together. So we can have our P of xi, it has to be less than or equal to 1, greater than equal to 0. So we have this constraint on our probability mass function. And furthermore, if we have a subset of all the possible values of x, then the probability that x takes any of these values is given by the following. So we'll write that out. So say, for example, we have that x, a random variable, has a subset. So A is a subset of x. Okay? So if A is a subset of all the possible values of x, then the probability that x takes a value of A is given as the sum where our possible values xi are an element of A, so they must be part of that set of A, and then we have P of xi. So now we're just considering a smaller subset. So it's essentially the same definition, but now there's an additional constraint such that we're only looking at this subset A, which is a subset of the values of x. So then we're just taking a sum of all the possible values that exist within that subset. Okay, so this is, again, our probability mass function, and these are all of its properties. So now we're going to shift over, and we are going to look at the probability density functions. So probability density functions, they're related to continuous random variables. So the probability density function is denoted as f, and it's of a continuous random variable. So for probability mass functions, to reiterate, was discrete. probability density functions are used in conjunction with continuous random variables. So this probability density function must satisfy 4 main properties. So the first property is that our f of x must be greater or equal to 0 for all x element of R. So for all the x on the real line, our probability density function must be greater than 0. Our second restriction, or second thing that it has to satisfy, is that f is piecewise continuous. So what does piecewise continuous mean? So I have a previous video which talks about continuity. However, piecewise continuous means that the function must be continuous on each of its intervals specified. So it's possible that it can be a piecewise function, which generally for the definition of continuity would not be continuous, but piecewise continuous means that it's continuous on that piecewise segment for all segments, okay? And then the third thing that it must satisfy is that if we take the integral from negative infinity to infinity of our probability density function, and we're integrating here, you can see, with respect to x, this must equal to 1. So this is kind of the sister property with the probability mass function, where if we add all the probabilities, they have to equal to 1. However, here, since we have continuous random variables, we're dealing with an integration because we want to know what is the area under the curve. So if we have our PDF over here, let's say this is our f of x, that means that the whole area under the curve of the function has to equal to 1. Okay, so that is kind of how we're representing the probability there. And lastly, our fourth thing that it can satisfy is that we can also consider a subset of probabilities. So say we're looking at what is the probability that our random variable x is greater than or equal to a and less than and equal to b. So we can write that as an integral with integration bounds. So instead of going from negative infinity to infinity, we can now go from a lower bound of a to an upper bound of b, of f of x, and again dx. So if we're looking at a picture, again, we might have our function f over here, and we are looking at specific bounds from a to b, and that means that to get that probability where x is between a and b, we're looking at that area under the curve from a to b. Okay, so those are all the those are the 4 things that it has to satisfy to be a PDF. And in my following videos, I'm going to show some more examples with real functions and how this is applied, so definitely stay tuned. And please subscribe so you can stay up to date to all the videos. If you enjoyed this one, please drop a like and don't be afraid to put any comments below, and I'd be happy to get back to you as soon as possible. And I look forward to seeing you next time.